order of business, I believe that I mentioned that in-person classroom participation is required, and yet people are still having the impression that they can attend every lecture online. That ends next week. There are 3 people in this class, and as far as I'm concerned, there should be a max of 10 students in this class, with some names I am seeing virtually. Now, unless you have reached out to me and explained why this is the case, this is not a virtual class. I explained this before the class started. For the statistics options in LeoNet, there were virtual options, and this is a face-to-face class. This is face-to-face with virtual alternatives to account for capacity issues. So starting next week, I am limiting the Google Meets for only people who are supposed to be attending virtually based off your group. I have the groups posted under course documents, just to make sure everyone can see. So under course documents, I have the groups. I believe I have everyone's preferences here. So starting next week, Group A will have to attend in person, and you will not be allowed to attend virtually. The link will be restricted for those emails. So again, this is not a virtual class. If you had me last semester, this is different because the class codes have changed. This is face-to-face, and I am adamant this semester about in-class participation. You can show up both days if you'd like, but last semester the attendance was really bad. Other departments are doing this as well. So I am forcing in-class attendance starting next week, unless you email me and explain why you cannot come to class. Other than that, I will expect you here. Additionally, the recording of the lectures will be restricted only to people who actually attend class. As you know, I post my lectures on YouTube, but I also can set the videos to private and only allow the videos to be seen by particular email addresses, so particular Gmail accounts. It looks like I will, in this current capacity, it looks like I will have to start doing that as well. So these are things to encourage your participation. This is something that will help you in the long run. This is things that other departments, other classes are doing as well. So starting next week, you have to attend in person when your group is supposed to attend in person. And if you don't, you're not here. If you're not, you don't get a link to the lecture unless you email me and explain what your situation is. So I suppose with that explained, let's go ahead and move on to the material, the new material, which is organizing quantitative data. So, and for those of you who are virtual, you better be close. I'm going to be asking a lot of input from you all. So there's going to be a lot of class participation here. So in this section, we're going to be summarizing quantitative data as opposed to qualitative data, which was the previous section. So in the previous section, we talked about qualitative data being categorical, and we simply just count the number of occurrences of each category. In this section, we look at quantitative data, and we talked about how quantitative data, which merely represents, that just represents numbers that can be added or subtracted, such as how much money you make, your age, distance, time. And so quantitative data can also be discrete or continuous, which may determine which way we analyze the data. If the data is discrete, which means if the data is countable, generally, so as you might see in the next example, the number of siblings you have, that is quantitative because the number of siblings, you can add 3 to 1, and then you say you have 4 siblings. You can add and subtract, and there's still a relationship there. But it is discrete because the number of siblings is countable. It's a very clearly distinguished thing. And so, so if we have discrete data with relatively few different values, such as my example with the number of siblings, then we're going to treat it just like we did in the previous section. We're going to treat the number of siblings or any other small discrete data as a frequency counter. We'll just count the number of occurrences, and it acts the same exact way as if all those numbers were categories. And so as you can see, I'm going to ask you all momentarily how many siblings you have, and we're going to build some information based off of that. If the data is discrete with many values, so generally discrete with many values, this could be a spread of ages from the age of 13 to 65. So instead of counting each individual age, sometimes you care about a range of ages. Sometimes you care about teenagers, and then young adults, and then middle-aged adults, and you want to clump them together as such. Or if the data is continuous. So something that could be continuous is distance. Values that generally have decimals. Then we have to create the categories ourselves using intervals. So it'd be one thing to just count every individual age, or we can count the number of ages in a range, as we'll see in an example, actually a few examples later on. But you count the number of occurrences in an interval of values, and then that's the frequency you put down. You count the number of occurrences within each interval, ultimately. And I'm going to do, so that's 3 different examples. That's discrete with relatively few values. That's going to be example 1. Discrete with many values. I have an example down here for that. So I'm going to go through each one of these one by one and show an example of each one. Because wording, just arduous wording, it'd be nice to complement that with some example. So bringing us exactly to example 1, we're going to create a histogram. So last section we talked about a bar graph. A histogram is pretty much a bar graph where the bars touch. You might think, well, that's not very interesting. It's when the categories actually are related to each other, and now the bars can sort of flow from one to the next instead of categorical, where everything is so uniquely determined or distinct rather. And so, and this is where I'm going to gauge the numbers from you all. So I guess as we did before. If you're virtual, just type whatever number, however many siblings you have. If you're in class, I'll go ahead and get that number from you. So how many do you? You have 2. Let me start writing these down. I'll have my, there's no smart ink on here. There's no smart ink. That's interesting. It's never happened before. It's there. It's so weird. Let's try this again. All right, technical difficulties. So weird. Oh, this is fun. Technology. Well, there's only one thing I can do. You all take 5, shutting down the computer. All right. I'll be back in this Google Meet, so you all hang tight. All right, I'm back. So present my screen again. Everyone can hear me, cool. We're still recording. All right. So for those of you who were virtual, go ahead and type your number again for the number of siblings you have. And then let's try this again. As virtual people do that, how many siblings do you have?
2.
You have 2. Jordan? 2. 5, you said?
Mm-hmm.
You have 1. I'll throw my hat in the mix. I only have 1. Okay, cool. And then I'll start getting everyone's numbers. We'll start with 0, 0, 0, 0. There's 1 only child here. So I counted 1 person with no siblings. Well, 1 sibling. 1, 2, 3, 4. In addition to 2, that'd be 6. You have 2 siblings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's keep going. 3 siblings. 1. Okay. 4 siblings. I think I saw a few. 1, 2, 3. I think there's only one with 5 or more. Yes. Okay. So then 1. Okay, so here's the counts of everybody in this class. 18, 19, 20, 21, 22, 23. Okay, good. So that's pretty good numbers to work with here. So, yeah, you virtual people stick around. I got a lot more classroom input I'm going to need in these later problems. So let's figure out the relative frequencies. So remember, the relative frequencies, well, you need to know how many numbers there are total. So let's see, that's 11, 12, 18, 19, 23. 23 total. Just put that there. And then the relative frequencies, 1 divided by 23, 6 divided by 23, and then we go on and on. 1 divided by 23, 3. Then we're just going to figure out all these numbers right fast. And generally, we like to leave the proportion form. You can interpret it as a percent if you'd like. Oops. 3, call it 0.04. I guess that answers these two down here. 0.04. 0.26 for that one. 0.48 for 2 siblings. 0.13. So this is telling us the spread. About half of the students in this class have 2 siblings, and then we're going to do some analysis on this simple question. So that's we've constructed a frequency and relative frequency distribution table, as we did in the last section. So notice we're treating the number of siblings, even though the number of siblings is a quantitative measure, because number of siblings, these are numbers, they're countable numbers, and there's only a small number of them. So we treat them as if they were categories. So really this doesn't change from the previous section. The only thing that changes is instead of a bar graph, we're going to use a histogram. And really there's honestly no difference other than the boxes touch. Because now the categories flow into each other. The categories are connected in some way. And notice this is a frequency histogram, not a relative frequency histogram. So we're going to be putting the numbers that we counted here, not the proportions. So for example, the number of people who are an only child that only have 1, I'll put a box that resembles just that. Pretty small box here. So this would be for 1. And sometimes what they do, and histograms and bar graphs alike, in addition to the box, they'll put the number that the box corresponds to on the top of it. Sometimes they'll do that. I'll do it here because it looks a little fancy. The number of people that have 1 sibling, that seems to be 6. And for no particular reason, I'm going to use a different color just to really emphasize this change. Notice the boxes touch. It's really the only difference between a bar graph and a histogram. Because now these categories, as I mentioned, flow into each other. That's 6. I'll use another color for the next one. 11. A little bit higher up here.
It's hard.
You two are very late.
Yeah. We got pulled over. And the cop took like 15 minutes.
Oh, now I'm curious. What did you get pulled over for? Speeding for this class? So did you get ticketed after all?
Yeah, and I have a court date this man.
Oh, no.
Well, you two will be just in time to participate in the next little survey I asked the class. So let's see, for this category, we counted 11. 3, there was only 1. So you two didn't miss much. I asked everybody how many siblings they had.
On Zoom.
Oh, really? Okay.
That's good.
That's what I call dedication. That's really impressive. I had a student show up the day after a bad car accident. He was in a full-on, cast and bandages and stuff, and he was there in class.
Wow.
He was so high on painkillers, I could tell, but he was there. Give him props. So 4 siblings, 3 people. So pretty standard stuff. And then 5 or more, we only had 1. So this is a frequency histogram. Really, I could have made this frequency histogram. I could zoom it in a lot more and make the highest value 15. That's if you use technology, just so you can really distinguish these a little bit better. Don't really like white space in your graph. You want it to be zoomed in as much as possible. But not being able to predict the number of siblings you all may have, I think this is good enough. So that's where we are at so far. And then it also goes on, we have a few questions in terms of the interpretation. What percentage of students have 1 sibling? Well, it's a good thing we know the relative frequencies. So 1 sibling, we just simply go up to the relative frequency for that. For siblings, the frequency is 0.26, so about 26%. About 26% of students in this class have 1 sibling. 26%. Part B, what percentage of students have 2 or more siblings? 2 or more, well, we don't have a proportion we don't have a category for 2 or more. We know 2, 3, 4, 5, and up. So how do we figure out that percentage?
Add up 2 and 5, like add up all the ones from 2 all the way to 5 and more.
Yeah, we can add. So we can do this one of 2 ways. And the way you're saying is perfectly fine. The percentage of students that have 2 or more siblings, we can add up 11, 1, 3, 1. So that's 16, and divide that by the total. Or we can add up the relative frequencies and then just get the percentage all at once. So you can add 0.48 plus 0.4 or 0.04 plus 0.13 plus 0.04, and then that'll tell you the percentage altogether. Either way should be fine. I guess I will do it the former way. So that would be 11 plus 1 plus 3 plus 1. Divide that by, let's say 23. Yeah, there's 23 people in total. So what did I say that was? That's 12, 15, 16 divided by 23. So I'll round it up to about, that's I'll round it up to 70. So that's about 70%. So about 70% of students have 2 or more siblings. And then part C, I was hoping that this graph would exhibit a little bit more distinguished shape. When I say skewed and have it italicized, this is really a means of asking, is the graph is the graph naturally coming down somewhat like a pyramid distribution, or is one side heavier than the other one? Does one side have particularly more values or stuff like that? And it definitely seems like the left side of this graph, a histogram or a bar graph, well, actually not a bar graph, that wouldn't be helpful, but a histogram helps tell you the spread of the distribution. And it seems to be that the left side is heavier here. So in other words, if you draw a shape around this, well, really it's going to do like this. It's got this tail on the right, as we'll talk about later. And we normally call this skewed to the right. This is really just this is just an interpretation for now. We'll define this in more concrete terms later. But the values tend to be dominant on the left in comparison to the right. So we'll say it's skewed to the right, and then we'll give that a more meaningful connotation or definition later. Okay. So that is a discrete variable that has a few values. We treat them as categories, as we did the previous section. The only new thing is now the bars touch, because now the categories are related to each other. Instead of male, female, prefer not to say, all the categories that are used in standard surveys. Does anyone have any questions before we progress? So each category in the previous example was an example of a class. So I'm going to be using that terminology. For discrete variables with many values and continuous variables, our classes are going to be represented by intervals. So now our categories, or the classes, as we move forward, will be represented by intervals, because it wouldn't be very practical to count the number of occurrences of one particular thing. As you could kind of foreshadow in example 2, if I counted all the occurrences of 74.2, that's the only time it occurs. So that wouldn't be very pragmatic of an approach. Instead, I want to figure out an interval of values, say like for grades. Generally, we use a 10-point grading scale. Normally, I want to find all the grades in a particular interval, and then I count how many things occur in that interval. But not to get too far ahead of myself, a class is a category into which data is grouped. So if I say class, just means the categories. When the classes are represented as intervals, there's some terminology the homework will ask you. So class or categories, the lower class limit is the smallest value within the class, or the smallest value in a category. This one. So if I said, what's the smallest value in the second class? Again, let's kind of foreshadow a bit. Here's the intervals over here. The lower class limit for the second class, well, here's the second one, because that's the second category, and there's the lower one. That's it. The second class is the second category, and the lower class limit is just the lower part of the interval.
So how is that one the lowest?
Because it's smaller than 89.9.
Okay.
You're only comparing these two.
Okay, I got you.
And then the highest one, or yeah, the upper class limit, as you would imagine, that's going to be the other one. So that's kind of the terminology they use. So the one I underlined in purple, that would be an example of a lower class limit for that class. And then the one I underlined in red would be an example of an upper class limit for that class. It's just a way to distinguish between the smallest and largest value in a particular interval. They also define the class width, and that is the difference between consecutive lower class limits. In other words, it's going to be the width of your boxes. So that would be the difference between 80 and 90, or 70 and 80. So here or it would be the difference between, say, 40 and 50, or 50 and 60, which would just be 10. To give an idea of what all of this terminology, and I have a few questions that will reiterate this for the problems that we are going to see. So we're going to do a few examples and identify all these things for data sets we actually create. So, all right, so example 2, here's the grades for actually a random math class I taught one of my first semesters here. So, yeah, so here's just a collection of grades. And so in this situation, I already gave the intervals from the table below. The reason why, the motivation why, is because, like I said before, all right, if we try to approach this categorically, count all the times that 74.2 show up. Obviously once. Count all the times 88.6 shows up. Well, that's only once. That's not very practical. So these are technically discrete. So this example would be an example of a discrete variable with many values. So it's technically discrete because these grade point averages do stop at a certain spot. It could also be interpreted as continuous, but we're not going to talk about that. We're not going to get it. That's really not a big deal. We treat them the same exact way. But instead of trying to count the frequency of these very specific numbers, we want an interval. We want an interval, and that way we can count the number of occurrences for which these data values occur in that interval. So you might already see what I'm talking about. You might not. We're going to take this table though, and really we're just going to count all the grades that are in between 90 and 100. So guess what? We got to go through this. Maybe you all can help me out and make sure I don't miss one. For 90 through 100, I believe I see 2. And then the 80s. So notice the categories are already given here. They're pretty much situated like grade point averages. So all the grades that are 80s, 1, 2, 3. In fact, I'll just start crossing them out as I go. 3, 4, 5, 6. 6. And then 70s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 60s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. One, 2, 3, 4, 5, 6. And 1. This is a post-COVID college algebra class. So there were. This is not a Math 105 or Math 241 class, so I don't feel as though I'm a difficult teacher. If you had me for Math 105, maybe you could or could not vouch for me in that regard. Jordan, I hope you vouch for me.
Oh, yeah. Hey, there's two of
So
the
we can figure out the relative frequencies.
49s.
So let's see what the total is. So let's see, 6 and 14, 20, 32, 38, 39. Wait, 39. Should be a composite. Oh, I missed a 40. Oops, there's another 40 over there. Okay. That couldn't be a prime number. 2 and 40. 2 divided by 40, 6 divided by 40, 10 divided by 40. Well, that one's easy, 0.25. 14 divided by 40, 6 divided by 40, 2 divided by 40. What's the first one? 0.05? Yes. 0.05. Same thing down here. 0.15, 0.15, and 0.35. So here's the frequency and relative frequency distribution table. But notice we're not doing this merely off of the categorical values, but instead we're doing this off of intervals. Now, in practice, you have to create these intervals on your own. These intervals may not be completely intuitive or just handed to you. Seeing your spread of data, you may have to break them up in a certain way and determine what the intervals are so you see a meaningful spread. Again, this is normally done with ages when you want to figure out age demographics for, say, how often a certain service is used, or say how often, or I guess the demographics at a university. So from here, we're going to quickly go ahead and construct a frequency histogram, but there's going to be a difference between this histogram and the previous one. A pretty significant difference that seems very subtle. I'm going to scroll up to the first histogram. So the first histogram, notice how the bar was right above 0. Here, the bar was right above 1, and the bar was right above 2. That's because we were counting the number of occurrences of 0, 1, and 2. In this histogram we're going to have, the bars are going to be adjacent. So they're not on top of the numbers, but the bar is defined with boundaries by the interval that we chose. So notice the 40 to 49.9. That would represent our first one. So notice there's a bit of a shift here, and I guess I can make that a little bit larger. So that would be 2 in that range. So notice the shift is it seems like a minute detail, but this is a clear distinction because now we're counting values that occur in an interval, not the number of occurrences of, say, 40 or 50, but number of occurrences in that interval. And then going from 50 to 59.9, let's see, that was 6. So about 6, call it right here. Again, you don't have to use different colors. I'm just doing this to identify the boxes. Next one is 14. So that's 14. Next one is 10. And then 6 and 2. And finally 2. Okay, so that is a frequency histogram. We could have also made a relative frequency histogram based off of the proportions found, but the shape would be the exact same. Frequency and a relative frequency graph are going to look the exact same, just different numbers. So here's the here's the frequency histogram, and this gives us a good idea about the spread. It gives us a good illustration about the spread of the data, and as it spreads from the mean, which we will talk about later, another day. So the first question is, what is the class width? And we define the class width as the difference between consecutive lower class limits, which means what are lower class limits? So what is the class width?
10.
It is 10. In one regard, it's just the width of your boxes. So this difference it's just the difference between any two of those intervals you choose. You can do that anywhere you want on this histogram, and it'll be the exact same. So that's 10. Identify the classes and their frequencies. So the classes, remember, that's the intervals that we chose in the table. These are the classes, 90 to 100, 80 to 89.9. We would just be writing all of those down again. So 90 to 100 with a frequency of, well, however many things occurred. 2. Only 2 things occurred in that interval. And you write them all. I'm not going to write all of them because it gets redundant pretty fast. 80 to 89.9 is the next one with a frequency of, well, however many things occurred in that interval, which seems to be 6. I'll just put ETC. You just write down the rest of them and their frequencies. Which class have the highest frequency? It's pretty easy. We go to our table. Which one had the highest frequency? 60 to 69.9. Because there was 14 occurrences in that interval. 60 to 69.9. Which class had the lowest frequency? There's kind of a tie. There's 2 of them that have the lowest frequency. 40 to 49.9 and 90 to 100. Those 2 both had a frequency of 2. What percentage of students had at least a 70% in the class? Again, we can do this in one of 2 ways. So the question is, what percent of students had at least a 70%? We can count everything after 70% because at least we can add up the 10, the 6, and the 2 and divide by the total amount. The 6, and the 2, and divide by the 40. So the 10 students had 70 to 79.9, 6 students had 80 to 89.9, and 2 had 90 to 100. So add up all of these, that's 18 divided by 40, and that's 0.45 or 45%. And then finally, is the graph skewed? It's that question again. Is the distribution leaning predominantly heavy on one particular side, or does the spread of information look pretty well distributed? Really, we're looking at this shape right here. And no, there's not really a skew of data. There's not really a left or right side that's overpowering in comparison to its other side. In other words, we're able to draw a nice bell shape, which will come up later. You might have already heard, if you might know what I'm talking about, but we were able to draw a nice bell shape when we trace out the outline of the histogram. So, no. No, bell shape. Does anyone have any questions up to here? So that last one was an example of discrete data that had a lot of distinct values, which motivated us to count the frequencies using intervals rather than count the occurrences of each one of these specific values. Example 3 is going to look at continuous data. Now, I think I'm pretty proud of this example. So when I was sitting around last night thinking, what can I ask them to really engage them? So example 3, I'm going to ask all of you, it's going to be in a rare feat to take out your phones. You have them turned off, turn them back on. I want you to go to your, so what I want you to do is go to your maps, whatever app you use for your apps, and determine the distance it is from campus or to campus. So just figure out the distance from your house if you're in here. Just figure out the distance, and I want to know how many miles it says. That's all I care about. I don't want to know where you live. I want to see how many miles, and I'm just going to start collecting numbers, online people. So if you're online, if you're at home, figure out the distance to Southeastern. If you're at Southeastern, figure out the distance to home. Whenever you figure out that number, then go ahead and does it give a decimal place as well? If so, I want to know the decimal as well. I want to know very specifically. Yeah, so 1.7 miles, that's kind of more what I would like to see. So Google Maps, see how well this works. Let's just pretend I live at Red, White, and Brew in Hammond, because I don't want you all to know my address. It's 1.4 miles. That's what I would put. So 1.4 miles for me. I'm hoping everyone in class has theirs. So if you have a decimal, please tell me the decimal as well. I want to get a nice realistic perspective of this. So we're going to start off by listing the distances. I'm going to start with you.
7.8.
7.8. Jordan, you have yours?
Yeah, 16.
Just 16? I mean, so that's fine, but well, you figure that out next.
Mine's literally 1.
1.
30.
30?
28.
28?
1.1.
1.1. All right, and what was the one I just saw for mine? I already forgot. Mine says 1.4. And now let's start writing down online people stuff. Let's see. 21.2, 42.7, 35.3.
Mine's actually 19 miles. 18 to 16 to 19. I
Cool.
can't get a decimal point, I don't know why.
That's okay. Maybe it's on the dot.
Yeah, mine's 30 on the dot.
Yeah, that's perfectly okay.
That's one.
1.7, 45. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 14. Let's keep going. So another 40. It's a 45 and a 37 and a 1.5. And then the last few. 21, a 34, and a 29. Hopefully I didn't count anybody twice, but that should be it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay. So here's the numbers a little bit larger. And so now, notice I didn't put any intervals. Because guess what? We need to figure out the intervals. So what would make sense for the intervals here? So this it's not an exact answer on what the intervals are. I'm not looking for a perfect answer. I'm looking for really what would be realistic to show a reasonable spread of these values. What would be a nice interval? Said every 10 miles. So how would we write those intervals? So we'll just pretend like we'll just start completely from scratch. We're going to start with the smallest values. So what would your first interval just look like? Going off of that amount you said.
Like 1 to 9.9.
So you're saying 1 to 9.9,
And then 10 to 19.9.
10 to 19.9, and then pretty much in that fashion, sure. 20 to 29.9. So this isn't really, so yeah, the number of intervals, and I said you may need more rows. We could have used less if everyone just, that would have been horrible for my statistical analysis if everyone lived a mile away. We just have one box that just shot straight up. That'd be horrible. This would be a horrible example I chose then. So let's do 30 to 39.9, 40 to 49.9. I think didn't we have 150 or am I? Yes, we do have 150. Okay. Well, that's quite a commute. 50 to 59.9. Okay, cool. So just perfectly worked out to where the number of rows is just spot on. So what we're going to do, well, we're going to determine the frequency within each one of these. So just going to count how many occurrences. And actually, there is a slight issue I have with one of these intervals. Does anyone happen to see it? And why I might have an issue with it? Just one of them. We would only have to change one little thing.
Which one?
Why?
Put it 0, because some might live less than a mile away.
We're going to put 0. I mean, that in this situation, we don't have anybody who lives within a mile,
Right?
but it's the class widths. We want the distances to be the same. So 0 to 10 is 10. 10 to 20 is 10. We want that to be the same. And that's the definition of a histogram. Now in practice, you don't need a histogram to do this, but in this class, the book, or at least in this context, the book says the histogram is going to always have equal widths of the bars, so we'll just acquiesce in that manner. And from here, we're going to really just count the number of occurrences. So pretty simple stuff. 0 to 9.9. Is that a 7 and an 8?
It's 7.8.
7.8. Oh, where's the decimal? 7.8. Okay, cool. So that's 1, 2, 3. Is that 14 or 1.4? See, I,
That's one point
That's
four,
one
it's
point
yours.
four.
where did these dots go? 21.2, I'd imagine. Okay, that was weird. I think the rest of them are spot on. Okay, let's try that again. 7.8, 1, 1.1, 1.4, 1.7, 1.5, that's 6. My counting's off, just let me know. 10 to 19.9. See a 19. Now let's keep going. Just 1. Okay. 20 to 29.9. 1, 2, 3, 4. 30 to 39.9. 1, 2, 3, 4, 5. Next one's in the 40s. 1, 2, 3, 4. And then 50 to 59.9. I believe there was only 1. Did I get everybody? Did I count that correctly? That's 10, 15, 21 values. Did I miss one?
No, that's everything.
That's everything? Cool. Okay. And let's go ahead and figure out the relative frequencies as well. So what's the total here? I think I just said 21. So that'd be 6 divided by 21, 1 divided by 21, 4, 5, 4 again, and 1 again. 6 divided by 21, 0 point, we'll call that 29, 0, 5, and that one can also go here. 0.19, 0.19, 0.24. So honestly, the spread's looking, well, let me not spoil the wording quite yet. I'm actually glad this happened. I think that's going to work out very nicely in tying this together with the next thing. All right, so from this table, we're going to go ahead and construct the frequency and relative frequency histograms from this. So notice they're completely blank. That's what that means. We have to fill them in. We have to figure out what to fill in. Because in our graphs, we're not going to be putting, say, 9.9. We're going to put 0, 10, 20. We're going to put the lower class linking, what do they call it? Limits. Lower class limits as the places to separate our y-axis. So 0, 10, 20, 30, 40, 50. That will be the x-axis. And really, it's going to be the same for this one over here as well. And it might not be perfect since we're drawing it, but that's okay. We also want to figure out the y-axis for the frequency. The y-axis for the frequency. So let's see, some of these values range anywhere from 1 to 6. So 6 being the highest. Let's make 1, 2, 3, 4, 5, 6. Because 6 is the highest frequency count. And then for each category, see 614, six is the first one. 1 is the next one. 2, 3, 4. So 6, 1, 4, 5, 4, 1. Six, 1, 4. All right. That's 60. Oops. 60, 60. And then 5, 4, 1. Okay, cool. 5, 4. And you can fill them in if you want. Let's do that. So that would be the frequency histogram. Just the number of times something occurs in an interval. Notice the bars are not directly over a particular number because we're not counting the number of occurrences of that number. We're counting the number of occurrences between, say, 0 and 10, and between 10 and 20. That's what this histogram is representing. So notice the bars are in between those. That's the distinction between categorical frequency counting and interval category frequencies. And the relative frequencies, so we just measure the proportions over here. See, the largest one is about 0.3. So we'll split this up. 0.1, 0.2, 0.3. This is the largest one, is about 0.29. And we do the same thing, but we use the relative frequencies. We use those decimal proportions that we found. I believe the first one was 0.29. The next one was 0.05. So it's going to be right halfway. 0.19. Maybe a little bit lower. 0.19. Oops. 0.24, 0.19, 0.05. And so notice the shapes are exactly the same in relation to each other. the size of the boxes relative to each other should not change. It's still the same spread of information, just represented in a different way. Just depends on if you want to know the count, the number of occurrences, the raw number, or if you want to know the proportions instead. You don't care how many people participated, you just want to know the percentages. All right, and we have a few questions relating to this, such as how many classes are there? How many categories did we measure by? So let's see, 0 to 10, or well, 0 to 9.9. So basically, how many different boxes do we have? 1, 2, 3, 4, 5, 6. 6 classes. Basically, how many different intervals did we utilize here? 6. What is the lower class limit for the second class? What is the upper class limit for that same class? So the second class, let's look at our table. Here's the second class, because it's second row. The lower class limit is the smaller one, 10. Upper class limit is the higher one, 19.9. So that's it. That's what you have to do to figure that out. 10 and 19.9 for the second class. What is the class width? Class width, the width of the particular boxes, or the difference between any consecutive lower class limits. So in other words, what's the difference between any two values here on the x-axis? Just 10. So that's how you figure out the class width. And I left part G blank because I had no idea what to expect. Let me choose between 20 and 40 miles. What percentage of students commute between 20 and 40 miles? Well, let's see. That's 4 plus 5. Because between 20 and 40 miles, between 20 and 40 miles, just count 4 and 5. And then we can divide that by the number we had in total, which was 21. So this is 4 plus 5 divided by 21. 9 divided by 21. So 0.43, or 43% of students commute between 20 and 40 miles. And then finally, is the data skewed? This is an interesting question because, I mean, it's mostly uniform, or not uniform, that's the wrong word. It's mostly evenly distributed, and then this one side completely just takes over. I don't really know. It's not really a skew, so to speak. I mean, if anything, you would say it's skewed to the right, because the right side of the middle peak is larger. But I would say it's not distinctive. It's not really distinctive. You could say it's skewed to the right, but that's based off of this one overzealous interval. Generally, that in statistics doesn't mean there's a skew. It's not, I don't necessarily think that's a fair representation. What people would normally do is probably break down that category into subcategories and see how that spread affects things. It's not distinctive. I'm not saying there is a skew or is not a skew. I'm just saying it's not the most definitive thing that we could just state as you know, make a statement about it. And so to bring this idea of skewed data into perspective, I guess the first question is, anyone have any questions? So to sort of give a more concrete idea as to the shape of a distribution, I guess to get all of these in the frame at the same time. So here's an example of the four different types of shapes. And they're, as you can tell, graph A, each one is illustrated below. So B is B, and of course you could just keep going. C is this one. D is of course this one. So there's different types of spreads. A uniform distribution is where all the bins or all the boxes are pretty much the same. The most important one is a bell-shaped distribution, which is B, where if you trace along the outer parts of the boxes, you tend to get a bell shape. This is normally a very natural occurrence in many different facets of statistical analysis. Pretty much the majority of classes that when teachers look at statistics of classes, generally this is the case with the C grades being the most common and the smaller values spreading out from the mean. Now distributions could also have a tail. So notice if I try to draw that same shape, it starts to curve off with this little tail right here. Works the same way on this one as well. When the data is dominant or inferior on one side relative to the peak. And this tail will determine a skew right or a skew left. So the skew is in the direction of the tail, which is what I wrote at the top. If the tail's on the right, then we're skewed to the right. On the left, it's skewed to the left. And a good example of this, here's Instagram users worldwide by age group. Notice this is skewed to the right because generally Instagram is used by young people. Not so much by, I guess I fall into that age group. I do not use Instagram. So these observations come up a lot. And then finally, I could probably talk about stem and leaf plots right fast. It's a way of organizing a bunch of data into a table, into a particular chart. Here I got all the ages of actors who won the Academy Award for Best Actor. And to put this in a stem and leaf plot, the stem would be the first number of each digit. So let's see. First numbers tend to be 3, 4, 5, 2. So there's a 2, I see a 3, I see a 4, a 5. Yeah, there's a 6. Are there any 7s? I don't think I see any 7s. So the first digit would be the stem, and then the leaf would be, so it works out kind of weird. So 29, I think, is the only one I see. So you'd put the second digit here. This might make more sense with the 30s. 30, 30, 30. So for some of those, a 2, a 7, and an 8. So notice I'm putting the second digit, and I'm just putting them. Normally you organize these. So you would put 2s and stuff, but see 36. So then you'd put the 6 part, 37 and 38. There's a 7 and an 8, a 9. Yeah, you put however many relative to the number of occurrences you see. And then the 4s, you do that the same. the 2, the 5, the 6, 0, 7, 3, 5, 8, 4, 1, 1, 5, 4, 2, blah, 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 and then 6 is less. And you can do this to also see the spread of information. So that's a stem and leaf plot. That is all the time I have. The homework for this, let's aim for that to be done Friday.
We don't have homework tonight? Okay.
Well, let's find out.
We do.
There is a homework for qualitative
Okay.
that's due, tonight. The qualitative homework's due tonight. The quantitative homework, we'll make that due Friday. Then once you do that, then just check your due dates.
Have a good day.
Take care.